from WPI to give this seminar. So his expertise is on numerical analysis, and now an expert on physics-informed neural networks.
Actually, I want to correct you. So I'm not yet expert in physics-informed neural network. There are too many issues to be addressed. I'm still learning. So actually, I want to discuss with you, and also thanks for the morning discussions. I learned, some of the problems can be explained here. So today I'm going to talk about some of the issues we met in training the physics-informed neural networks. Okay, so basically concerned from the scaling point of view. So we'll talk about two problems. One is the singular perspective problems, and another one is the high-dimensional problems. And of course, well, I would like to thank you for the invitation, and happy to be here. It's been maybe 10 years, almost 10 years, 6 years. Okay, all right. So I'm going to just a brief introduction to the physics-informed neural networks. So the physics-informed neural networks is nothing but least square collocation method. Okay, so people think about the equations. Usually, this actually people abstracted them from physics. So this is where the name physics come from. And well, so basically, the first step, try to understand the physics-informed networks is try to formulate the problems as a minimization problem. So you will see that think about even the first simple one, the two-point boundary value problem. So you can formulate it as a minimization problem. So basically, what we use is the residual equation, negative Laplace u minus f. If this guy equal to 0, and the boundary is actually also put in as the so-called loss function. So if everything is 0, then the equation should be satisfied. Of course, mathematically we can make it rigorous. So say in what conditions for u to be the classical solution or weak solution or this kind of thing. But for practitioners, people care about how do we solve this? Okay, after the AlphaGo, right? So because of the powerful tools of in machine learning, so people consider why not using neural networks to solve them. And this formulation here is fairly standard. This collocation method. So I will talk about where's the collocation come from, and basically you will convert it to the optimization problem, and then you will, because everything here is except this two boundary point, so you actually have the L2 norm, so you have to use some numerical integration or Monte Carlo method to sample the integration, and then you will have something discrete to solve with. And if you use U with finite difference method, finite element method, this is going to be least square finite element method. And if you use U with the neural networks, this is the physics-informed neural networks. Okay. So in this way here, so this actually conceptually is very simple, but the application is very wide. The thing is because you can easily put some data as in the object function or the loss function, so that you can minimize the whole thing. So you get some minimizer, or quasi minimizer, or whatever that is close to them. So you can get some solution. And basically, if you have data and the physics is pretty efficient. Okay, so if you simply just have physics, you can actually have you want to have no data, then you simply work with the PDEs. Okay. If you have data, without physics, you can still work with data. So basically, this is the least square regression. But this is really balanced. If you have data, if you have model, you can combine together. So this is very convenient form. And also you can, if you have some something that is to be inferred, for example, if you don't know F, but you have some data, you can put the minimization over F and also put some data over there. You can actually have almost the same formulation. Okay, so And because of all this, Python packages, they actually included all this auto differentiation, so that you can make this training the calculation with derivatives much easier. Well, maybe not easier, but make it as possible. For us to calculate it, then we can use the gradient descent method, or some other method to work on them. Okay, so this is the one of the biggest application of this is the pin formulations for the inverse problem. Okay, so but to solve the inverse problem, we have to make sure the forward problem should be solved correctly. So this is why people have been exploring efficient method for forward problems. Okay, so this framework is very simple and very user friendly, especially for students. So compared to the classical method, right? So you need mesh, you need to carefully design the schemes. You have to carefully define the mesh. You have to do a lot of things. You need to learn numerical linear algebra, try to form linear systems, and you have to solve it correctly. Try to watch out, what the solver will bring to you. So, but in the machine learning method, like the pin formulations, what you do is just do the random collocation, try to describe the L2 norm, and the rest is try to call some Python package, and then you solve the PDE. Okay. So basically, you can have any undergrad who knows multivariate calculus and linear algebra and a little bit of ODE, PDE. So as long as they know the multivariate calculus, you can have them work on PDE on surface within 2 weeks. Okay. Solve them. So this is a very short learning curve. So of course you need to learn how to call the packages, and then you probably a little bit of tuning, but it's still very, very short time. It's a learning curve. Okay, so compared with the classical numerical method, this is actually the big plus for the training. Okay. Often people, especially undergrad, would all think about we have ChatGPT, right? So 4 or 5, and even more powerful AI. So why do we have to learn so many courses? Try to just solve one equation. Well, maybe it takes 2 years to set up the basic knowledge. So all this, this is one of the education side of this machine learning method. Of course, there are many, many applications. So all this depends on, so basically a machine learning method is so we have the pin formulation, which is the design of one of the ways to design the loss functions. And we will train them using the fixed point iteration method, like the gradient descent method. And we will train them on CPUs and GPUs. And of course, you have to have some resources, right? This is very high energy consumption. So consumption here. So this is all the aspect of the machine learning method. So, but on the human side, okay, we do have very short learning curve. Okay, well, today I'm going to focus on one issue that looks like a very promising approach to solve PDEs. So one of this issue is depends on the training method, because the neural networks becomes a little bit more complicated than what we usually have in optimization. So usually, if we use the gradient descent method or stochastic gradient descent method, these are low order method. They can resolve only low frequency solutions and a small gradient. Okay, so this is the problem. So of course, people will be thinking about the networks, changing the networks, changing their loss function, or modify the training method a little bit. All this kind of work has been done. So, but without just use feed-forward networks may not work for solutions with high frequencies and small gradient, for large gradient, like the sharp transitions. Okay. So today I'm going to talk about two approaches we have been working on, try to resolve some of the scaling issues, some of the high frequency or the large gradient problems. The first one I want to discuss is the steady state Fokker-Planck equations in high dimensions. Basically here we are changing the feed-forward neural networks to using tensor instead of the directly applying the neural networks, the feed-forward neural networks. So the problems of this is, if you have a Fokker-Planck equation, so if you initialize, usually this is by Gaussian, so you will have something like this. And, this is actually, on the left, this is the initial guess. If you realize, try to sample randomly initialize the weight and bias, so you can get this roughly Gaussian. Well, but the true density is like this. So you will have, several modes. If you look at on the right, so you see that even they are mode, they have large values, but the large values are not really significantly large. So for example, the yellow ones represent 10 to the -2, okay? The blue ones actually is 10 to the -3, something like this. So you still see these scales, the large values and the small values, but they are comparably not too close. And how to solve them in high dimensions, right? So this is actually a big issue. The problem we're thinking about, this is a steady state Fokker-Planck equations corresponding to some stochastic differential equations with drift F and with differential coefficient sigma. To make the Fokker-Planck equation to be well posed, so we need the we would find the positive solutions, non-negative solutions with integration to 1. So there are some existence uniqueness of this density functions. But for now, I'm going to say, okay, I assume this equation has some solutions we're interested in. And later on, we will test some of the special cases where we know the exact solution. Okay. If without any data here, we are solving the problems in RD. So the first problem we encounter is, you have to solve problems in unbounded domain. So usually this will require some numerical support to try to fix some bounded domain so that we can solve the problem. Okay. Often this scaling will be a big issue. So somewhere you have large values, somewhere you have very small values, but these small values contribute to the density. Okay, so that this density integration equal to 1. So you cannot really ignore them. So, but how do this? This is actually something very tricky. And also, even if you have just do approximations in high dimensions, what do you do? Okay, suppose you are not solving the PDE. You are actually approximating the high dimensional Gauss distribution function, density function. So you have e to the, you have something like this. Even the simplest one. So, this thing here make the solution actually very focused. When the radius of x is not too large, but the thing here, if you have d here, so make the whole thing is very small. Okay, so this is when you have larger d, you have smaller scale, and then how do you resolve them? So today we actually only maybe half step or one step towards this direction. So we're going to solve up to 10-dimensional problems. Okay. And another thing is, if we try to use neural networks to approximate P, so eventually, we will need to integrate this networks over the domain RD or the numerical spot we are focusing on. But this is not really easy because the networks can behave, differently, in different places. You cannot really address this numerical integration. Probably you can think of using monte-Carlo method, but the monte-Carlo method also has its drawbacks, like high variance region. You cannot really do it well, and you cannot really use the classical quadrature rules, because the classical quadrature rules usually like to have some smooth solution. So all this, yeah.
Would you mind explain the scaling issue you referred to?
Yeah, the scaling issue is because one thing is even you have the peak, right? So think about a peak of the solution. If you think about the projections, you know, in 1D, this is looks okay. You have, for example, this is Gaussian, so this is the peak point is 1. So the rest is you truncate it somewhere. And okay, you say, okay, I'm probably good. So think about a Gaussian from -3 to +3, you'll be fine. Okay. But in high dimensional, if you look at just one dimension, this is not order 1 anymore. This is actually 10 to the -2. But the rest of the thing is 10 to the -3. Okay. So if you truncate somewhere, you should truncate it, you know, in a larger region so that you can incorporate these small scales. So if you use larger domains, so what will happen is, you know, you have to focus on the computation. So you have to use a lot of points to resolve this large region. So the computation cost will be very high. Okay. So also, as I said, so there are some numerical integrations. Also in high dimensions, how do you compute the derivatives? Okay. Well, you probably say use auto differentiation, but most Python packages use auto differentiation with tensor. So the implement with tensor means, you know, if you have many training points, then this is going to be the dimension would be the dimension of training points multiply the intrinsic dimension. Okay. So this requires lots of memory. Okay. So there are some approaches that try to avoid this kind of issues. Try to use try to avoid this auto differentiation. But the thing is, I'm going to use the second approach. I'm going to use the tensor neural networks to solve this, to approximate this. This is something we find very efficient. So we were going to use tensor, where you're going to use RBF networks instead, also with the feed-forward neural networks. Okay. Here are some references on the Fokker-Planck equations, but I'll just skip this. Try to focus on how to solve this using the physically informed neural networks. So first of all, the loss function. How do we minimize the Fokker-Planck equation? So here we use the Pn here. The Pn is not our solution, but the Pn normalized by the integration is our solution. So that we'll have a density function. We will ask the solution on this. What we call it numerical support omega will be approximately 1. So I cannot have this exact 1, but we will ask see on the rest of the domain. Okay, omega complement, this will be approximately 0. Okay, so this is the only way we can approximate, focus only on some numerical support. Okay. So what we do here is, okay, this is critical points. So I will show later on if you do not choose the tight support, so it's going to be very inefficient. Okay. So here what we do is, because we're considering tensor later on, so we're going to use Harper cube. Okay. So the thing is, what we do is, okay, how to find the numerical support. So we are going to find the corresponding SDE and then run some simulations, try to get some trajectory at the terminal points. Okay, and so what we have? So we have, so this is the equation we're working on. So this is going to be sigma x. Okay, we were going to run up to a certain time. For example, it's very large time, so that you get some trajectories, x1, x100 or 1,000. Okay, and because at the terminal point, I assume that they could somehow approximately is from the asymptotic, the steady state density function. So I will use a domain that covers this all the trajectory points. Okay, so this is very rough. Okay, but in many cases that works. Okay. So the point we want to have is, okay, because of this trajectory from stochastic differential equations, we're going to set up a Harper cube that contains all this trajectory. And of course, you can pick the center. You can find some numbers here. Try to see how we can set up this domain.
How do you choose the capital T?
The capital T, you just run long enough. Try to see there's no decay in the solution. That will be. Of course, you can try to you can make it a little bit finer argument. For example, if you know F, you know sigma, you know some of the mixing time, from MSCMC or whatever. This is something doable. Okay. And also the cost here is not really large. We actually use 10, 100, and 1,000 trajectories. Well, this should depends on the dimension also, of course. Okay. So usually with use 1,000, 10,000, this will be sufficient. Okay.
Hi there, we have a question from the audience that's online.
Okay, so let's see. Okay, let's see. Okay.
Can you see it? Otherwise, I can read it to you.
Okay, I can see this is about the scaling. Can you estimate the scale cheaply and then zoom out approximately? Well, in high dimensions, yes and no. In high dimensions, it will be not easy. The thing is because we don't have much choice. We don't have many choices to estimate this. One way I know that is you can run some SDEs, try to see get some density estimator, try to see which is the low density area, which is high density area, but that does not really give you the scale, scaling correctly. I'm not sure this answers the question. Okay, looks like
You can click answered.
okay. Oh, I'll consider that answered. Okay. Well, one thing I want to see is say about this. So this is the biggest step for us to try to estimate omega. And then the rest thing is solve this on the bounded domain. And then so here we're using the tensor neural networks. So basically, we are mimicking the how we approximate the density function. So if you have a dense function, suppose it's continuous, we can think about this as a py operated on with the integration of py with vector data function, and then you try to the data function can be treated as a tensor, and you can have something from the quadrature or Monte Carlo method, the quadrant Monte Carlo method, or whatever. So this summation here is the summation over there. So n usually we will call this in the tensor community they call it the rank. So of course this is not rank, but I will still use the name. So the n will be the rank, and then the rest, you can think about the rest will be the basis. The basis will be the tensor. For each way you have each dimension, you have a network, and you put the tensor together. So you will get the tensor neural networks. Of course, it gives the universal approximator. But the thing is, how do you train them? So I'm going to use two kind of tensor neural networks. The first one is every dimension you have a feed-forward neural network. The second one is linear combinations of kernel functions or the radial basis functions. The idea of this is using the multiple kernels because for the kernel functions, usually we do not use many layers, but we can use many kernels to sum them up. Okay. So we use the convex combinations of them, and so I want to again emphasize this tensor neural network. Because why do we choose this? The reason is because the cost is really reduced, and the memory requirement is reduced. Okay. Because somehow you can avoid auto differentiation even for RBF, you can avoid that, totally avoid that. to better train this kind of kernels functions, you actually have you make this h you want to control this h a little bit, try to see, okay, you can, because the h actually control the derivative of Kij. So if you control that, then you have better stable training. So you will be successful in training if the derivatives of the solution is not too large. Okay. So this is the motivation and the details for the neural networks. Okay. So so I'm going to show some numeric examples, and also here I'm going to use simply the exact solutions. The reason for this is, okay, there are not many benchmark tests in high dimensions. You have to somehow to fabricate or make up some solutions that make sense to Fokker-Planck equation. Okay, so this is actually a very classical. We use the gradient system. We will try to see using the metric here. So it looks like the relative errors, but here we actually look at the aggregation of this relative errors. So not just look at one point, because what we are interested in is the high probability region instead of just a few points. Okay, so because you think about a very high dimensions, a few points doesn't really make much difference. Okay, okay, so I'm going to show this example one here. So the example one, you see that the first line is actually, you have the three-way interactions, x1, x2, x1, x3, and x2, x3. And the second line is just to introduce some complexity. Try to see this is not exactly exponential. You have some, because they have exponential of h, so this is going to be some polynomial in front of exponential. Okay. So the reason we use this is because in addition to the three-way interaction, we have 8 modes. Okay, so this is you can figure out by taking the derivative equal to 0. So in this case, we can figure out the domain is from -0.5 to 0.5. This is the Harvard cube. So this is initialization. We use this RBF, tensor RBF, and then the true state is on the left, and the estimation is on the right. Okay, you see that in this case is not really bad, because the solution here is actually 2.24. Okay, and this one here is 0.03. Okay, you can still have some high, and the larger scale a little bit. Of course, this is the 2D projection from 3 dimensions. So one thing I want to check, this is the criteria. We want to evaluate the metric. So the first line means, okay, we want to test. First, we pick, this is 500K test point, and I want to see that at this point, is the exact solution larger than a certain value? And if this is the case, we pick up all the points and try to see the aggregated area, the aggregated relative error. Okay, so you see that only about 20% of points actually are larger than 10 to the -3. This is the first column. Okay, so and you can actually get 10 to the 5%. This is relative error. This is a 5% relative error. So this is not really bad. Of course, you can check, even high probability regions. So, for example, the solutions, the exact solutions has values larger than 0.1. So you will have 4% of error for these points. And you see that the number of points is very, very much smaller, much less than the point that has the values larger than 10 to the -3. Okay.
What optimizer are you using here?
We are using the atoms. We use a standard one. So what we change is the difference is the loss function and also the tensor RBF. Okay. So the rest will be what is called the pin formulation. I think I will skip one of the problem. So So here are these some examples. We actually I want to showcase this this 10-dimensional ones. So again, you know, we try to find something that's non-trivial. Okay, so in high dimensions, but you know, all the cases we find in high dimensions are either linear or kernel functions or tensor product. So that's why we make up this this function, try to have some well, through at least through interactions. You can think about the solutions actually are through product of 3-dimensional functions. Okay, but this is you know, of course this is not the best, but you know, that's the best we can think of. You know, so in this case, 10 dimensions. In this case, I said, you know, the way we choose this domain is not really efficient because you have to have very tight support so that you can work on this domain. Because this is 10-dimensional, this is you need a lot of sampling points. So again, so this is projected the mode, so you can observe this. So fairly good. Well, of course, in this case, I still have the solutions 10 to the, 0.224 and 0.21. So this is a little bit off. You have kind of a 10 to the -2 error. So this is the test. So in this case, because we have relatively high probability value, so we actually have, you know, the relative errors. The aggregated relative error is not so bad. It's 5%. But you see that, you know, if you in 10 dimensions, you will find some values that is larger than 0.1. So you only have, you know, 200 points. Okay. So compared to all the test points, this is very little. Okay. So one thing I talked about so far is about the tensor neural networks, tensor RBF. The reason we use it because, you know, you can easily control the numerical integration. You can compute them efficiently, the derivatives. And, you know, what about the tensor feed forward? Okay. So I'm not saying the tensor feed forward is bad, but, you know, in this case, we have here is not really working well. This is actually something I learned, I borrowed from the, optimization solvers. I'm not sure this is called Rosenbrock, whatever, you know, open function. So basically you have x1 to the power 2. Well, I will change it to power 4 so that we have larger derivatives. And, you know, you combine this x1, x2, x3, x4, and x5, x6. So basically this is a tensor product of 2-dimensional functions. Okay. So in this case, you know, we can find the numerical support. You can use the procedure I just described to find this is -0.6 to 0.6 to the 6. This is within the error 10 to the -6. This is approximately 1. But if you make it a little bit, well, half of this interval, somehow you actually have, you know, not too bad, it's 0.44. So if you use this, actually, you can get much better result for the tensor feed forward. So I'm going to, well, this looks like a lot of data, but I'm going to choose maybe 3 rows. The first one is tensor RBF. You know, you choose 800 ranks, and you know the 3 means I'm using the 3 kernels in each dimension. So if I choose the support I just described, then you will see that this the errors is pretty. Oh well, this is not the best, but you know this is somehow satisfactory. Well, here actually you see that you know the solutions are. Here we use the p star actually larger than 0.05 instead of very small, very small threshold epsilon. So otherwise, the error will be very very rough. Okay. We try to test this with tensor feed forward. So for the tensor feed forward, we have many more choices because we have to choose the rank n. We have to choose the network size for each dimension. So, and also we need to test whether this is sensitive to the support or not. Okay. So I want to pick one, the first one and the last one. So we have 10, rank 10. So it looks like this is 20% error if we look at the first column of this error. Okay, and if we look at the last column, so last by 2 row, so we have 128 rank, and the very shallow neural networks in each dimension, you will see that the error is actually not so great. It's about 40% already. Okay. And also this is trained on a small support. If we choose on a larger support, okay, so it's actually kind of worse. Okay, or even you use very deep neural networks. Okay, so because of this complexity, right, you have to try out the network size and number of layers and number of neurons and also the rank. So this is all we have here. Okay, but it's already something which we can draw from. They can draw some conclusion from is so you need a really tight support. Okay, so even you sacrifice this integration, you order one a little bit, but you have to use a small. The reason is you have to make sure the integration, the numerical integration of tensor neural networks is calculated perfectly. So this is the big issue we find. Of course, we don't have any theory for this. This is about the tensor neural networks for Fokker-Planck equations. Okay. Any questions? No. Okay. All right. So I'm quickly summarize this, and so of course there are many limitations of this process. Of course, first of all, because we're now in domain, we need to in the numerical support. This requires the solution decays relatively fast. If the solution actually decays really slowly, you have to do something else. Okay, you cannot really expect the numerical support in this way will work. Okay, so so here, well, we don't have any theory. So do we have stability with the formulation? Do we have any estimate? Error estimate? No. Okay, so I will later on talk about why for the PIN formulations you have to have something like energy estimate. Okay, but we don't. So want to comment a little bit on the tensor IBF. So people think IBF is a bad method, but if you control the parameters well, if you use many kinds of kernels, the IBF actually you can get somehow stable training. Of course, you need some control on these parameters. So that somehow is a little bit ask for some skills. Okay, but the point is, the RBF, you will never expect higher accuracy from RBF. You will use the float 32, which is actually makes this computers really large, really faster. So it can avoid this auto differentiation, auto numerical integration. Okay, but the tensor feed-forward neural network sometimes you get a better accuracy, but you need the price you pay. You have to get accurate integration, and you have to have some balance between the network size and the rank. So that's really something, this is again another tuning to do. So this is the first part for the Fokker-Planck. Let's see if we have any questions. Oh, okay. Okay. Okay, all right, so not really questions. So this is the Fokker-Planck. Okay. So hopefully I described the main issues of the problems. I want to see if you have any comments, and also, we are desperately, asking for comments, suggestions, especially if one want to solve high dimensional problems, especially for those applications. If you have SDEs, you want to solve and find the density functions. you can easily find, 10 dimensions, 100 dimensions, even 1,000, million dimensions. Okay, so if you have, if you can access some of this, density functions, right, they will be very helpful for them. Yeah. Okay, so any comments? Nope. Okay, all right. I'm going to talk about low dimensional problems. So people think about, the pin for the physically informed networks for PDEs. People are saying, okay, well, is the formulation actually a replacement of a classical method? Well, clearly, the answer is very clear. No. Okay, this is not the intention of replacing any neural network. It's just, think about this is actually a easy, well, first of all, education side, ease of training students. Okay, another thing is, you can get somehow maybe quick and some reference solution, like what business people use machine learning for. Okay, to just get some consultants, get some issues. Okay, and but of course you want a little bit closer to the problem that you expect. Okay, so one thing we think about in low dimensions, the body scale problems, for example, the boundary layer problems and the interior layer problems, and also for the the sharp transitions. So what we do is think about this boundary layer problems. If you look at the solution on the left, right, along x equal to 1 and y equal to 1, so you have very sharp transitions. So this is actually the boundary layer. And well, of course, we have the exact solution in this case. We fabricate 1. And then in this case, f here, you see, is at 1, 1 here, f is f has a very sharp transition from the 2 to 0. So you will expect the derivative of f is very large. Okay. And later on, we'll talk about how to do this. Okay. Basically, okay, so the issue is the boundary layer. Well, means, okay, in a very thin region, so you're going to have large gradient. Okay. So as I said, so if you use the stochastic gradient descent method, you are not going to train this well, okay? Because, it only learns small gradient and low frequency solutions. Okay. So of course, there are many solutions for this. For high frequency, you can simply, well, if you have 5 high frequencies, why don't just learn the frequency? So this is the so-called feature method, Fourier feature method. And you can also use other methods. These are all intuitive methods. One thing we want to suggest, want to do instead is to try to mimic well, what people do in the scale expansion. Okay, so I know Professor Wang has the work on this scale expansion, try to use the pins of the solutions, the equations from the multiple the scale expansions, but we're not expert on the scale expansion. We try to use something simple. Okay, so this is the purpose of using physically informed neural networks. Okay. So the idea is we are going to use the N here is neural network. Okay. We're going to use well, if without the second and the third term, this is going to be the so this is going to be the standard neural network, feed-forward neural network. Okay. So well, if I want to pick up these scales, I'm going to use something. So x minus xc divided by square root of epsilon. Okay. So what I'm going to do is, okay, so because SGD or whatever training methods can only pick up the small derivatives, I want to make this explicit. Okay. I put XC here just to avoid that, for boundary layers, I don't want to use explicit solutions, auxiliary informations of this point here. So this, you can replace this with any points. And this one here, and the third one here is try to say, okay, because the inner layer is, so this will be, well, we use tangent H here. So this is the inner layer, okay? And well, if I do this, I'm going to have, so something here and something here. Well, I'm going to have actually two more arguments. So all these elements here, okay. So these are the element, the freedom I'm going to add. Okay, so what this does is, okay, I'm going to, well, because this is linear, and definitely you will shift this this x a little bit, you know, shift the x. Well, if you have different coefficient here, you're going to x minus something times xc. Okay, so this one here, we are going to actually pick up the right location of boundary of the layers, not necessarily boundary layers.
So XC, do you learn XC?
No,
or-
the xc is just you know, the center of the, it's easier to set up.
Yeah, but in the case if you have a moving interface layer.
Yeah, interface moving. This is another issue. So, okay. So then, well, if I have this, then the rest need to put into the least square collocation. You know, try to solve it. Okay. Well, it's simple enough. Well, look at this and, you know, pick up the right large gradient location, and also another analogy, well, intuition here is, okay, so if you think about this as a function of epsilon, this is actually pick up the scales of 1/square root of epsilon, and also all the integer orders, if n is smooth. So anyway, so the first, the most important intuition from us is this one here. You can explicitly pick up the gradient. Well, no matter what, this is going to be 1/square root of epsilon. You will pick up the scale, and you, well, hopefully you can get, you know, from the weight, you can try to figure out, you know, where's the large gradient. Okay. So this is the idea. Well, this is the explicit scale expansion. This is these are Professor Wang's work. So, and this one here. So there are other ways to do this, but you know, you have to have some knowledge of how to control them. But you know, you have to have actual decisions on where to stop. For example, in the multi-scale expansion, you know, you have to make sure where you truncate. You know, what is the right scale to pick up. Well, this is just to mention that, okay, you can deal with parabolic equations, and also, and then when this is elliptic problems, we're all going to work on. So this is the P formulations. Well, just look at here. So this is the residue of this equation, and this is the boundary and the initial condition, and also the red part here is we learn from the image processing, right? So you want to keep, if you want to keep the sharp transitions, you probably want to put some ingredients here. Okay? Of course, you can put the first order, you know, I mean the total variation here, with which gives out power 1. This here we use 2. We find it's working, but you know, you definitely can replace this with order 1, power 1 here. Okay. So the rest is then, okay, so the loss function is the same as in the P formulation. The second thing is, okay, you only change the boundary condition, the neural networks, the rest is the same. Okay. So I want to showcase this, and I found this example is very, very challenging for most of the P formulations. On the left, I plot the epsilon equal to 10 to the negative 2. Okay, you see that so you have these sharp transitions from around -1, +1, and if you have 10 to the negative 3, you almost have this vertical. The solution is almost 0 in the interior domain, and you know, on the boundary you have 1 and 2. Okay, you can check this is the derivatives here is going to be the order of 1/epsilon. Okay, so if you use the P formulation, you can get it with, for example, the millions of epochs, okay, with some adaptive weight on any whatever techniques you can apply. But you know, with this the peak scales, we use actually 50K epochs, and you can get pretty good result. So this is the solution for 10 to the negative 2. Okay, exact and the solution you can from inorm, right? So we cannot really discriminate them. Okay, but of course, if you zoom in, try to say, okay, so the errors could be very large on the negative on the left hand side. Okay, and okay, so so here, sorry, so the epochs is 20K actually. So, but you know what the challenge is here is if you try to think absolute 10 to the negative 3, you see on the left I plot the exact solution, the numerical solution. You see that numerical solution, the dashed black one, are actually a little bit of shift. So the reason is we cannot really resolve this region. Okay. So after discussion with Lee and also Jeff this morning, so I figured out the why. And I want to show you what happens on the right on this region here. On the left, on the right, when close to 1, so you see that the solutions actually shift a little bit. But the good thing is, you know, it is within 10 to the negative 2. Well, at the very beginning, we think this is somehow acceptable because no matter what you work with, right? So what the numerical method we work with, you always have this shift if you have a large gradient. If you have any experience with working the shock locations, try to capture the shock locations. So it is always the order of h, the step size. Okay, so you cannot really over there you have the shock location shift a little bit, then the error will be always order 1. I'm not aware of you know, the recent development in numerical method. Try to, if there are some smarter ways to avoid this. But you know, at least this is what I learned, you know, 10 years ago from Qi-Wangshu course. So this is what it is, and the reason for this is because we use the active function tangent h. Okay. The reason is. Oh, by the way, so tangent h is somehow standard choice for large transitions. Okay, but you know, for this problem, you know, with this scale, we cannot really do anything. So suppose I have the u minus f. So this is where we're going to minimize. So okay, a point. Okay, if we do this, you know, taking the gradient, make it 0, right? So this is somehow twice 2 Lu theta minus f, and this thing here was going to be, well, I'm going to use that as a gradient. So this is going to be Lu f theta. So of course this is going to be xj equal to 0. The summation of this equal to 0. Okay. So you see that if your theta actually satisfy the solution, well, this is going to be, well, satisfy the equation, this is going to be very close to 0. So then what happens here is, okay, so this one here looks like the gradient with respect to theta is, okay, is like somehow like the weight. Okay, so if you cannot get this weight correctly, then you know there's no way you can actually get this close. Okay, for example, if you have a vanishing gradient here, so there's no way you can get this correctly. Okay, if this is 0, well, probably there's some way, right? So if you're lucky enough to say, okay, this is happen to be 0, that could happen. But you know, the thing is, okay, if this is 0, and this is actually, you cannot really get this. So, well, unfortunately, this is the case for the gradient of the tangent h. So for example, if I think about the one layer, okay, just something here. So if we take the gradient, so this is going to be 1 minus tangent h squared, okay, which means, okay, this is 1 minus, this guy will be 1, then the thing here will be 0. Okay, then there's no way you can resolve this. I think this is probably one of this drawback of this physically informed neural networks, okay, because we use a residual. So almost time. So I think this is the showcase. I mean, This is very representative situation. This is something, this is probably everyone would test in a standard test benchmark problem for pin formulations. Okay, so you work with the, probably if you take numerical PDEs, this is also standard. So here we actually say, okay, if we put epsilon is very small, 10 to the -2 divided by pi here, so you're going to have shock later. For example, t equal to 1, so you get not shock. Sorry, this is definitely not shock. So this is shock transition at is x equal to 0. And if you shift the initial condition a little bit, you will have the shock transition at x equal to 0.5. So if you zoom in, you will see that the errors, these are the errors at t equal to 1. So here you will see that x equal to 1 here will have the largest error. So this is for the shift to x0 equal to 0. You have the sharp transition at x0 equal to 0. Okay. So I guess I can skip this. And so 1D examples, 2D examples. Okay. I want to see that this is not just only for the large gradient. This is also for high frequency. For the 2D Helmholtz equations, if you simply use pin formulation without Fourier feature or whatever, so you cannot really solve it. Well, this is not, you probably think this is not too much, in it, but this is a state art of pin formulation. Okay. The thing is, you cannot resolve the high frequencies, for example, k equal to 100. Okay. So this is somehow a challenge problem. Many people have different solutions. So our perspective is, okay, we want to take 1 over k squared as the small parameters, and we still use the scale, try to pick it up, the right solution. Looks like we can do the k equal to 100, sorry, not 100, k equal to 10. Okay. And of course, the errors looks not so great. This is actually 10 to the -2. And if you look at the relative errors, there are many places, of course, they are 0. Of course, this will be very large. Okay. But at least we get the solution looks correct. Okay. So they actually, you get 10 to the -2 absolute error. Okay. So this is about this guy here. What can we see about, in this case, we do have something to say about our estimate. So people always criticize, the pin formulations, the least square formulations cannot do anything. But, one thing here is I want to showcase, if you have a PDE stability, what it says, for example, this is 2-point boundary value problem. So if you use the least square formulation, minimize with back to the UN here. So you can use the PDE stability. So essentially what it says is, okay, the L2 norm of this, think about the U minus UN as 1 unit. So this is going to be the natural Laplacian works on the same. Think about this is V, this is Laplacian V, this is V at 1, this is V at -1. Okay. So this is exactly the PDE stability, the regularity of the solution. If you have the right-hand side is satisfied, and you have the boundary satisfied, you have the boundary and you have the right-hand side, you have control of this norm of the solution. Okay. So once you have that, the rest is, some basic inequalities. So basically it says, okay, so this is the formulation, and this is the pin loss, this is discretization. Remember, this is L2, and the pin formulation is nothing but discretization of this L2. Okay, so then the error can be controlled by, the pin loss. Well, this is whatever you get. And this is something from the discretization. So could it be numerical integration from a column method, the numerical integration, whatever. So this is the idea of the error estimate. Okay. Okay, so of course this is somehow good, but not really useful, because if you have some epsilon here, so the C would depend on epsilon. This becomes much more complicated to say anything about the convergence. Okay. But this is, in theory, you can make it more fancy, more complicated. So basically what it says, well, I'm not going to say this. basically what it says is if you have conditional stability, PDE stability, then you are going to have the pin formulation stability and RF. I guess I'll stop here. So just quick summary. Okay. Yep. So I'm not going to discuss this, but dealing with the scaling issues, okay, from the unbounded domain and also for some large gradient. So you need special treatment. This is, some field need to be explored. Okay. We need the wisdom from mathematical formulation that works well, probably work well for the classical method. And also we need some, much more deeper understanding, of the optimization method. Okay. But currently, Jeff asked me this morning, so do we have robust needs? So unfortunately, we don't. We need to know the problem well, and we have to have some lots of the benchmark tests so that we can see something that is robust, reliable. And so far, if you look at the error estimate, they are actually useful in terms of saying that okay, it works, the method should work, and didn't say anything about the training. Okay. So that's the current state of art. Okay. Okay, I will stop here.
Thanks. Any questions from audience?
Thanks for the talk. Maybe a question about the physical property of the solution, such as like the positivity. So first the part about the Fokker-Planck equation.
Yeah.
So I wonder if the solution from the neural network can always keep like the positive.
Yes. For tensor neural networks, for the feed-forward, we use soft class. You can use ReLU 3 or something, right? So for the RBF, this is straightforward. So if you pick positive definite ones, then you just take the positive combinations, then you will always have positive solutions. Okay.
This kind of is not always true for other types of neural network.
You can always apply the soft class. So means it's basically soft class is basically what is called the Gibbs distribution.
Okay.
So you take exponential and normalize. That's it.
Yeah. Thanks.
Any questions? If not, let's thank the speaker again.
Thank you for watching. Jeff, do you have any more comments?
Okay.
Oh, looks like
But I don't know.
Okay. So it looks like everyone left. So
Okay.
I'm going to stop sharing.
Thank you.
Believe